Moon is a planet or not? In the grand theater of the cosmos, where billions of celestial bodies dance in harmony, there is one object that has captured human imagination more than any other: the moon. For countless generations, humans have looked up at this glowing orb, weaving stories, myths, and scientific questions around its mysterious presence. But behind the beauty of its silvery light lies a fundamental question that still sparks curiosity in the minds of students, scientists, and dreamers alike. Is the moon a planet, or is it something else? This question may sound simple at first, but the answer requires us to dive into the deep definitions of astronomy, planetary science, and history itself. The moon is more than just Earth's companion. It is a celestial body with a complex identity that forces us to challenge how we classify the universe around us. To truly understand whether the moon can be called a planet, we must begin by revisiting the very definitions of celestial bodies. In astronomy, not everything that shines or orbits in space can be called a planet. There are moons, dwarf planets, asteroids, comets, and stars, all with their own unique characteristics. At first glance, the moon seems like it could qualify as a planet. It is spherical, has a layered interior with a crust, mantle, and core, and even exerts gravitational influence on Earth. In fact, if the moon orbited the sun directly instead of Earth, many scientists argue it would indeed be classified as a planet. And yet, because it orbits Earth, it is officially called a natural satellite. But why does this matter? Why debate whether the moon is a planet or not? The significance lies not only in scientific curiosity, but also in how humans understand their place in the cosmos. The moon is humanity's first stepping stone into space exploration. It influences tides, stabilizes Earth's tilt, and may have even been essential for life to flourish here. Understanding its classification is more than a technical debate. It is a journey into how humans define the universe and themselves. Before reaching a conclusion, we must explore several key areas: the definitions of a planet and a moon, the history of how astronomers have classified celestial bodies, the moon's formation, its physical properties, and its role in Earth's history. We must also consider the scientific arguments that suggest the moon could be treated like a planet, as well as the counterarguments that firmly reject this idea. Only then can we approach an informed answer to the question: is the moon a planet, or is it not? Long before telescopes revealed the secrets of the cosmos, ancient civilizations looked up at the moon and wondered what it truly was. To early humans, the moon was not just a celestial object but a source of mystery, inspiration, and even fear. It influenced calendars, guided farmers in planting and harvesting, and served as a light in the dark. For thousands of years, people did not differentiate between stars, planets, and moons. To them, anything that shone in the night sky was part of a divine tapestry. In this early period, the moon was often treated as a planetary body because there was no clear system of classification. The ancient Babylonians, Egyptians, Greeks, and Chinese all had their own myths about the moon. In many cultures, the moon was seen as a god or goddess, a living entity rather than a lifeless rock. The Greeks, for example, associated the moon with Artemis or Selene, while the Romans linked it to Diana. These mythological identities show that the moon was perceived as something more than just a satellite. It was a powerful celestial being. It was not until the classical age of philosophy that people began asking scientific questions about the moon. Philosophers like Aristotle suggested that the moon was a heavenly sphere made of a special, unchanging substance called ether, different from the corruptible materials found on Earth. At the same time, other thinkers such as Democritus speculated that the moon might be made of rock, perhaps even containing mountains and valleys. However, without telescopes, such ideas remained unproven. The turning point came with Nicholas Copernicus in the 16th century. His revolutionary heliocentric model placed the sun at the center of the universe instead of Earth. In this new picture of the cosmos, planets orbited the sun, while the moon orbited Earth. This was one of the earliest formal distinctions between a planet and a moon. Under this model, the moon lost its status as a possible planet and became Earth's satellite. Still, Copernicus's work did not settle the question completely. After all, people still debated whether Earth's moon should be considered a secondary planet. The debate intensified in the 17th century with the invention of the telescope. Galileo Galilei made one of the most important discoveries when he turned his telescope toward the moon in 1609. He observed craters, mountains, and shadows across its surface. The moon, once thought to be a perfect and smooth heavenly body, was revealed to be rugged and Earth-like. Galileo's findings shattered the Aristotelian idea of unchanging heavens and reinforced the idea that the moon was similar to a terrestrial planet. Yet, despite its planetary features, its position around Earth forced astronomers to call it a satellite. Later, the discovery of other moons around Jupiter by Galileo and his contemporaries expanded human understanding further. If Jupiter could have moons and Earth could have one, then moons were a separate category of celestial body, distinct from planets. This shifted the language of astronomy, and the moon officially became Earth's natural satellite, even though it still looked very much like a planet. By the 20th century, as astronomy became more precise, scientists began refining the definitions of planets, moons, and other objects in space. The International Astronomical Union, IAU, the official authority on naming and defining celestial objects, established criteria to determine what counts as a planet. Under this framework, the moon clearly did not qualify, but the debate never fully disappeared. Thus, history shows us that the moon's identity has evolved with human knowledge. From a god in the sky to a heavenly sphere, from a possible planet to a confirmed satellite, its classification has always reflected the limits of human understanding at the time. Yet, even today, with all our scientific advancements, the moon continues to defy simple labels. The question of whether the moon can be considered a planet cannot be answered without understanding what a planet actually is. In ancient times, the word planet simply meant a wandering star, describing bright objects that moved differently across the night sky compared to the fixed stars. But as astronomy matured, especially in the 20th and 21st centuries, scientists needed a more precise, universal definition. This need became especially urgent after the discovery of many Pluto-like objects beyond Neptune, forcing astronomers to reconsider the very meaning of the term planet. The International Astronomical Union, IAU, the organization responsible for naming and classifying celestial objects, took up the challenge. In 2006, they issued the most widely accepted modern definition of a planet. According to the IAU, for an object to be considered a planet in our solar system, it must meet 3 conditions. It must orbit the sun. A planet must revolve directly around the sun, not around another planet. This rule separates planets from moons. It must be massive enough to be nearly round, in hydrostatic equilibrium. Due to gravity, the object must have sufficient mass to pull itself into a roughly spherical shape, as opposed to irregularly shaped asteroids. It must have cleared the neighborhood around its orbit. This means the planet must dominate its orbital region by either consuming or gravitationally controlling smaller bodies nearby. If a celestial body meets all 3 of these conditions, it is officially recognized as a planet. However, if it fails one or more, it falls into other categories such as dwarf planet, moon, or small solar system body. Now, let's apply these criteria to the moon. Does the moon orbit the sun directly?
No.
The moon orbits Earth, which in turn orbits the sun. This alone disqualifies it from being a planet under the IU definition. Is the moon spherical in shape?
Yes.
The moon has sufficient mass and gravity to maintain a nearly round shape, just like planets do. This criterion is satisfied. Has the moon cleared its neighborhood? Not really. Since it does not orbit the sun independently, this rule doesn't even apply directly. Instead, its orbit is tied to Earth's gravitational dominance. By this measure, the moon fails the very first requirement, which is the most fundamental. It does not orbit the sun. For this reason, the IU and astronomers worldwide classify the moon as a natural satellite, not a planet. But the story does not end here. Some scientists argue that the IU's definition is too narrow and that it excludes bodies like the moon, which are planetary in nature, but do not orbit the sun directly. These scientists suggest that classification should be based more on physical characteristics, size, shape, and geology, rather than orbital mechanics. After all, The moon has mountains, valleys, volcanic plains, and even a differentiated core, mantle, and crust just like Earth. From a geological perspective, the moon behaves very much like a planet. Thus, while the IU's criteria are clear, they do not fully capture the complexities of celestial bodies. This leaves open a gray area where some argue that the moon could be called a planetary satellite, a hybrid term acknowledging its planetary traits while still recognizing its orbit around Earth. This scientific debate highlights that the classification of celestial bodies is not only about science, but also about human-made definitions. Nature does not neatly fit into our categories. Instead, we create categories to make sense of nature. The moon sits at the crossroads of these definitions, forcing us to reconsider whether our labels truly reflect its reality. If someone were to study the moon without knowing its orbit, they might easily mistake it for a planet. The moon has many of the same physical and geological characteristics that define the terrestrial planets in our solar system: Mercury, Venus, Earth, and Mars. In fact, in terms of its structure, composition, and history, the moon shares more similarities with planets than with smaller, irregular bodies like asteroids or comets. The moon is not an irregular lump of rock like many of the small asteroids in the solar system. Instead, it is a nearly spherical body, with a diameter of about 3,474 kilometers, roughly one-fourth the size of Earth. This spherical shape results from its strong gravitational pull, which forced it into hydrostatic equilibrium. This property alone gives the moon a planetary quality, as it satisfies one of the key conditions used to classify planets. Like Earth and other rocky planets, the moon has a differentiated interior, meaning its internal layers are separated by density. Scientists believe it has a small iron-rich core, a mantle of silicate rock, and a crust made mostly of oxygen, silicon, magnesium, and aluminum. The existence of a layered structure suggests that, during its formation, the moon experienced intense heating and partial melting, processes characteristic of planet formation. The moon's surface is marked by a fascinating variety of geological features. Impact craters. Billions of years of asteroid and comet impacts have left scars across its surface, some enormous in size. The most famous, like Tycho and Copernicus craters, are visible even with the naked eye from Earth. Maria, plural of mare, these are the dark, basaltic plains formed by ancient volcanic activity. The smooth Maria contrast with the heavily cratered highlands, showing a history of internal activity. Mountains and valleys. The moon has high mountain ranges, such as the Montes Apenninus, which rival the Great Ranges on Earth. Rills and faults. Long channels and fractures suggest tectonic-like processes once shaped its surface. These features strongly resemble those found on terrestrial planets, further blurring the line between the moon and planets. Although the moon is no longer geologically active in a major way, evidence shows it once had intense volcanic eruptions. The Maria were formed when molten lava flooded large basins about 3 to 4 billion years ago. While the moon lacks the plate tectonics of Earth, its crust still exhibits fractures and evidence of ancient tectonic stresses. This again reflects a planetary history rather than the simpler geology of small moons or asteroids. Unlike planets such as Earth or Venus, the moon does not have a thick atmosphere. However, it does possess a thin exosphere composed of helium, argon, sodium, and trace elements. Though extremely tenuous, this exosphere demonstrates that the moon interacts with solar radiation and cosmic particles in ways similar to planets with more substantial atmospheres. Despite its small size, the moon exerts significant gravitational force, not only keeping itself round but also affecting Earth. Its gravity is responsible for tides in Earth's oceans, which in turn play a crucial role in regulating Earth's ecosystems. Such influence is a characteristic usually associated with planets, not small satellites. A striking fact is that the moon is not much smaller than Mercury, the smallest planet in our solar system. Mercury is about 4,880 kilometers in diameter, only about 1.4 times larger than the moon. Yet Mercury is classified as a planet while the moon is not, showing that the distinction is not based solely on size or geology but rather on orbital dynamics. Taken together, these features illustrate why many scientists consider the moon to have a planetary nature. It is spherical, layered, geologically complex, and influential in its gravitational effects. If the moon orbited the sun instead of Earth, by almost all physical measures, it would likely be called a planet. And this is where the debate intensifies. Is the moon's classification as a satellite simply a matter of perspective, or does it reflect a deeper scientific truth? The story of the moon's origin is as dramatic and mysterious as the question of its identity. How the moon came into existence is not only important to planetary science, but also central to the debate over whether it should be regarded as a planet. Unlike artificial satellites, which humans place into orbit, the moon is a natural satellite born from the chaotic early history of the solar system. Several theories have been proposed over the centuries, but the most widely accepted today is the giant impact hypothesis. In the past, scientists put forward three major ideas about how the moon may have formed. Capture theory. This suggested that the moon was once an independent celestial body, possibly a planetesimal or small planet, that wandered too close to Earth. Earth's gravity captured it, pulling it into orbit. If this theory were true, it would make sense to view the moon as a former planet in its own right. However, the differences in chemical composition between Earth and the moon make this theory less likely. Fission theory. This proposed that the moon was once part of Earth itself. According to this view, a massive chunk of molten Earth was flung off by rapid rotation, eventually forming the moon. This would mean the moon was essentially born from Earth, almost like a twin. But Earth does not spin fast enough to support this theory, making it improbable. Co-formation theory. This suggested that Earth and the moon formed side by side from the same region of the solar nebula. In this scenario, the moon would be a kind of sibling planet to Earth, forming in the same neighborhood. However, this theory cannot explain the differences in density and core size between the two bodies. Today, the most widely accepted explanation is the giant impact hypothesis. According to this model, about 4.5 billion years ago, a Mars-sized body, often referred to as Theia, collided with the early Earth. The impact was catastrophic, blasting huge amounts of molten rock and debris into orbit around Earth. Over time, this material coalesced and cooled, forming what we now call the moon. This theory explains several key observations. The moon's composition is strikingly similar to Earth's outer layers, suggesting they share a common origin. The moon has a smaller iron core compared to Earth, consistent with the idea that it was formed mostly from Earth's crust and mantle material rather than from Theia's metallic core. The angular momentum of the Earth-Moon system fits well with the results of such a massive collision. The origin of the moon directly influences how we think about it. If the capture theory were correct, we could argue that the moon was once an independent planetary body, demoted to satellite status only because it fell under Earth's gravitational influence. If the co-formation theory were true, the moon might be considered a kind of double planet with Earth, similar to how Pluto and its moon Charon are sometimes described as a binary system. Under the giant impact hypothesis, the moon is born of Earth itself, a planetary fragment that took on a planetary nature of its own. It is not simply a piece of space debris, but a world formed through the same violent processes that created planets. In this sense, the moon could be thought of as Earth's daughter planet, although conventionally we call it a satellite. Some astronomers argue that the Earth-Moon pair should be classified as a double planet system. A double planet occurs when two celestial bodies of comparable size orbit a common center of mass. In the case of Earth and the moon, the center of mass, the barycenter, is located inside Earth, but not at its core. It lies about 1,700 kilometers beneath Earth's surface. Because the moon is so large relative to Earth, unlike most other planetary moons, the Earth-Moon system behaves differently from typical planet-moon pairs. Pluto and Charon are already considered a binary dwarf planet system by many scientists. If Pluto-Charon is treated this way, why not Earth and the moon? This argument reinforces the idea that the moon has planetary status in all but name. The moon's violent birth also raises philosophical questions. If it was formed from the same materials as Earth, shares a planetary structure, and plays a fundamental role in shaping Earth's environment, then why deny it planetary recognition? The only reason lies in its orbit around Earth, a technical detail that may not fully capture its planetary essence. Thus, The moon's origin story, whether as a captured body, a sibling, or Earth's child born of a cosmic collision, adds weight to the argument that the moon is more than a mere satellite. It is a body with a planetary past and planetary features, forever linked to Earth's fate. The moon is not just a silent companion in Earth's night sky. Its presence has profoundly shaped the history of our planet, influencing everything from the stability of Earth's rotation to the emergence and evolution of life itself. These influences go far beyond what we normally expect from a satellite and make the moon resemble a co-planet in its impact on Earth's destiny. One of the most critical roles of the moon is stabilizing Earth's axial tilt. Earth is tilted about 23.5 degrees, which gives us seasons. Without the moon, this tilt could vary wildly over millions of years, swinging between extreme angles due to gravitational interactions with other planets. Such instability would cause catastrophic climate shifts, making Earth less hospitable for life. The moon's gravitational pull acts as an anchor, keeping Earth's tilt steady and ensuring a relatively stable climate. This stabilizing effect is a planetary scale influence, far greater than what any ordinary satellite exerts on its host planet. The daily rhythm of ocean tides is directly controlled by the moon's gravitational pull. Tides are not just a fascinating natural phenomenon, they play a crucial role in Earth's ecosystems. Early in Earth's history, tides may have helped life emerge by creating shallow tidal pools where organic molecules could concentrate and interact. Over billions of years, tides have shaped coastlines, influenced weather patterns, and driven the migration and behavior of countless species. The moon's gravitational influence on Earth's oceans demonstrates how deeply connected it is to the planet's biosphere. The moon is gradually slowing down Earth's rotation through tidal friction. Billions of years ago, a day on Earth was only about 5 to 6 hours long. Today, it is 24 hours, and this lengthening process continues at a slow pace as angular momentum is transferred from Earth to the moon, pushing the moon farther away by about 3.8 centimeters per year. This interaction illustrates that Earth and the moon are locked in a dynamic, evolving relationship more characteristic of a double planetary system than a simple planet-moon pair. The moon also acts as a cosmic shield. While not as massive as Jupiter in deflecting comets and asteroids, the moon has absorbed countless impacts that might otherwise have struck Earth. Its cratered surface is evidence of this bombardment. By taking the brunt of some collisions, the moon may have spared Earth from destructive impacts, contributing to the stability necessary for life to thrive. The moon's role is not only physical but also cultural and psychological. From ancient myths to modern science, the moon has guided human imagination and exploration. Calendars, agricultural cycles, and navigation systems were all influenced by the moon's cycles. Even today, it inspires poets, scientists, and spacefarers alike. This cultural significance elevates the moon from being just another satellite to a planet-like companion whose presence is deeply woven into human civilization. In modern times, the moon has become humanity's first stepping stone into space. The Apollo missions of the 1960s and 1970s transformed it from a distant object of wonder into a tangible world that humans could set foot upon. Its potential as a base for future missions to Mars or beyond reinforces its planetary identity. The moon is not merely a satellite but a world in its own right, with landscapes, resources, and a place in humanity's future. When we compare Earth's moon to other moons in the solar system, such as Jupiter's Io or Saturn's Titan, its planetary qualities become even clearer. Titan has an atmosphere thicker than Earth's, and Io is volcanically active. These moons are often described as worlds in their own right, despite being classified as satellites. By this standard, Earth's moon is equally deserving of such recognition. In all these ways, stabilizing Earth, shaping tides, influencing rotation, protecting against impacts, inspiring culture, and offering a platform for exploration, the moon exerts a planet-like role that transcends its technical classification as a satellite. It acts less like a passive follower and more like an active partner in Earth's planetary system.